So the next presenter is Aaron Polensky. So he will continue the same approach for a different chemical reaction.
Yeah. So my research kind of approached the same kind of concept except where I was looking at.
Let me complete the introduction. When in this list of possible research projects, this project was labeled by initials Dr. AP because the idea came from Dr. Alex Parent. And Aaron Polensky recognized it as it is a prompt to use his initials, which are also AP.
Yeah. So I was this was a reaction between a metal hydroxide and a carbon chain to form a carbonyl and a carbon chain to form a hydroxide and a charged carbon. And so it was just to analyze to see due to the charged carbon being formed and with the hydroxide is not entirely stable. And so to get as much of that produced as you can, I was analyzing the transfer of the hydrogen from the chain to form the hydroxide. And so that's what we did here. So this is the coding that I used right away. So for my, Alright, so for the mass, it is going to be that of just the single hydrogen that we were looking at because that's the only thing that's being transferred and moved around from the carbon chain to the metal. And then I changed, the P naught is what I changed at different points of the time. So I started at, I think I've had at 0.1 and I went all the way up to like 10 or something. And that's just the different energy levels that was used. And then there's something else. Oh yeah. The width of them is the wavelengths converted into atomic units. One is for the hydroxyl group and the other one is for the carbon chain. And then that's all I was going to talk about this. Next I have the actual data that was collected. Oh, you can't see it all, but that's okay. What's really important is the temperatures, I guess you could say. So I started with the 0.1 and I went all the way to 20 actually. 10 and 20 are at the bottom there. And so with the raw data, the slope is the production of the actual products. And as the temperature or as the energy was continually increased, the slope did continually increase. What I found though is that this really did not, even though yes it did yield more, some of the temperatures really aren't actually plausible. So I came to the conclusion that temperature like at 81 Kelvin, probably the most like realistic temperature that would actually make the reaction go at an increased rate. I mean, anything else, you could tone it in a little more and actually find a reasonable value for your energy level. But I mean, I don't think any of us are going to get to 32,000 Kelvin anytime soon. So, and then I have some videos of the P naught at 1, or the energy at 1, I should say. And so you can just see that as the reaction continues, it will slowly, continually try to create the products, but then also at the same time, if you would like keep the energy level consistent, which it is, and you would run it for a longer period of time, it'll hit an equilibrium, and it'll just go back and forth and create and destroy the products and just keep going all the way. And then, here's a P naught of 10. This one you actually saw a lot more product actually formed because of the higher energy level. I think you can start to see it getting into the equilibrium at the end though, but I really just ignored that and only just focused on the beginning part of the data because no time can you ever have a consistent energy of anything like that. So that is the graphs for those. Oh, is there any question?
Okay, let's thank Aaron.